Imagine a solid block of aluminum.
Okay, got
Now,
it.
just imagine a spinning blade violently slicing through that metal at like 40 meters a minute.
Yeah, which is incredibly fast.
Right. And doing it with microscopic precision, 24 hours a day. I mean, conceptually, we tend to think of machining aluminum as, relatively straightforward
Yeah,
because it's a softer metal.
right, like cutting butter with a hot knife.
Exactly. You just carve away what you don't need.
Yeah.
But the physics required to execute that thousands of times a shift without the machine literally shaking itself apart or melting down, it turns that simple concept into a massive logistical nightmare.
Oh, absolutely. It's a tremendous engineering hurdle. I mean, taking raw material and turning it into a perfect component over and over again at that speed, it requires a complete rethinking of how industrial machinery actually moves.
Yeah.
Because the gap between carving, say, a single prototype and running a high-speed mass production line is just entirely dictated by physics.
Okay, well, let's unpack this. Because in today's deep dive, we're looking at a highly technical piece of engineering documentation. And it focuses on something called the Moving Beam GMC.
Which stands for Gantry Machining Center.
Right. So our mission today, for you listening, is to explore the hidden mechanics of mass production. Specifically, why manufacturing aluminum alloys at a global scale requires this very specific architecture.
Yeah, and how it solves some pretty wild, invisible forces that constantly threaten to ruin the metal.
Exactly. So where do we start?
Well, what's fascinating here is that the entire architectural solution really comes down to one of the most uncompromising laws of physics,
It is.
inertia. It all boils down to the structural difference between moving a heavy, unpredictable table versus moving a lightweight, highly predictable beam.
Okay, so it's a structural thing.
Yeah, exactly. If you want to achieve blistering acceleration while maintaining, sub-millimeter precision, the foundational rule of the moving beam gantry is that you must keep the heavy workpiece absolutely still.
And just move the lighter parts around it.
Precisely. You only move the machine parts.
So let's visualize the traditional alternative just to really understand why that matters.
Right.
Like in a conventional setup, a moving table machine, you have a massive cast iron bed.
Right.
You take your raw aluminum block, you bolt it to that table, and the machine's drive motors have to physically shove that entire table, plus the metal, back and forth underneath a stationary cutting tool.
Yeah, which is a lot of mass to throw around.
Exactly. So exactly how much of a problem is that extra weight?
Well, it fundamentally limits everything the machine can do. I mean, a moving table has to carry every single kilogram of the workpiece. And in mass production, that workpiece is a variable.
Oh, right. Because you're not always making the same part.
Exactly. On a Tuesday, you might be machining a small internal bracket for a car door, but on a Wednesday, you might be carving out a massive structural aerospace panel.
Wow. Okay.
So the total moving mass is entirely dependent on the job, which means the machine's motors are constantly fighting a completely different amount of physical resistance.
So the acceleration profile is always compromised then.
Yeah.
I mean, you can't tune the motors for peak performance because peak performance literally changes depending on what's bolted to the table.
Exactly. That changing load drastically slows down acceleration. But the deeper issue is actually stability.
Stability.
Yeah. When you strap a massive asymmetrical aluminum plate to a moving table, its center of gravity is, well, it's rarely aligned perfectly with the machine's drive mechanisms.
Oh, I see. It's off-center.
Right. So when that massive table rapidly accelerates, stops, and reverses direction, which it does constantly, during milling, the off-center weight creates a massive inertial load.
Okay.
The engineering term for this is an overturning moment.
An overturning moment. Wow. That paints a pretty violent picture.
Yeah.
It sounds like the machine is literally trying to torque itself off the floor every time it changes direction.
That is essentially the invisible force at play, yeah. The kinetic energy of the heavy table wants to keep moving, but the motor is suddenly yanking it backward. Yeah, it generates a tremendous amount of mechanical reversal shock. And because the payload weight is always a variable, it's virtually impossible to lock in perfectly stable production parameters in the control software.
You're just perpetually settling for a middle ground compromise.
Exactly. The moving beam GMC, however, completely circumvents this.
Because the setup is inverted.
Right.
With a moving beam, the table is just cast into the foundation. It doesn't move. The aluminum block just sits there.
Yes.
And the machine features a bridge, the gantry, or the beam that glides smoothly over the top of the metal, carrying the cutting spindle.
Yeah, and the structural brilliance of that design is that the moving mass, so the gantry bridge and the spindle assembly, is relatively light. And critically, it is constant.
It doesn't change.
Never. It does not matter if the machine is carving a 10-pound block or a 1,000-pound block. The drive system only ever moves the exact same mass.
Okay, I have to push back on the real-world scale of this, though. I'm imagining a massive, multi-million-dollar factory floor. If we're just shaving off like fractions of a second per movement by pushing a lighter beam instead of a heavy table, does it actually impact the bottom line?
You'd be surprised.
I mean, it feels a bit like trying to improve a semi-truck's fuel efficiency by taking the floor mats out of the cab.
Well, it's a fair critique until you run the math on high-volume production.
Okay, let's hear the math.
We aren't just talking about the time the tool is physically slicing metal. A machining center executes thousands of non-cutting moves every single hour.
Oh, right. Like moving between cuts.
Exactly. These are called rapid traverses. The machine pulls the tool up, zips across a 3-foot expanse of aluminum to start a new hole pattern, then darts over to the tool carousel to swap a drill bit for a milling cutter.
It's constantly darting around in empty space.
All day long. Now, if you save just 0.2 of a second on every single positioning move because the beam can accelerate instantly, that tiny fraction compounds.
Because it's doing it thousands of times.
Right. Over the course of thousands of tool changes and millions of positioning moves across tens of thousands of parts, those fractions of a second aggregate into days or even weeks of reclaimed production capacity over a fiscal year.
Wow. Weeks of extra production time, just from the floor mats.
Exactly. But the advantages extend far beyond the stopwatch. It's largely about mechanical survival.
Meaning the physical degradation of the machine itself.
Oh, just imagine you're painting a massive wall for 8 hours straight.
Yeah.
If you're using a heavy, waterlogged wooden brush, your shoulder's going to be screaming by the afternoon.
Oh, for sure.
But if someone swaps that out for a featherlight carbon fiber brush, the sheer amount of kinetic energy your joints save is enormous. The machine experiences the exact same relief.
That makes total sense.
Lower inertial force translates directly to significantly less stress and friction on the internal guideways, the ball screws, and the servo motors. So the moving beam doesn't just shave time, it drastically extends the operational lifespan of the equipment.
Here's where it gets really interesting, though, because everything we just discussed is about straight line speed, right? Just getting from point A to point B.
Yeah.
But manufacturing is rarely just straight lines. The sources dive heavily into this concept of high-feed contouring, which is essentially the cornering problem.
Yeah, this is crucial. Aluminum requires incredibly aggressive feed rates to be machined efficiently. We are talking about the tool traveling through solid metal at 20 to 40 meters per minute.
But traveling at 40 meters a minute is completely useless if the machine can't control its own momentum.
Right.
Think about driving a winding mountain road. If you are in a lightweight, low-to-the-ground sports car, you can fly down a straightaway, brake at the very last possible millisecond, whip around a tight hairpin corner, and immediately punch the gas again.
Because you have low mass.
Exactly. You hug the asphalt perfectly.
Yeah, the low inertia allows the tires and the brakes to easily overpower the forward momentum.
Right. Now, put a fully loaded 80,000-pound dump truck on that exact same road going the exact same speed.
That's a terrifying image.
Right. The dump truck might have a massive engine to get it up to 60 miles an hour. But when it hits that sharp corner, physics just takes over. You slam on the brakes, turn the steering wheel, and the sheer, unstoppable mass of that truck pushes it in a straight line, completely ignoring the steering, right off the cliff.
Yeah, and that phenomenon translates directly to high-speed machining. When a machine has high-axis inertia, like a heavy-moving table, the control software is reading the blueprint and telling the motors, execute a sharp 90-degree right turn right now.
And it can't.
No, the physical mechanics simply cannot react as fast as the digital command. The sheer mass of the table physically keeps moving forward for a fraction of a millisecond after the motor tries to stop it.
So the tool literally drifts off the programmed path and carves into metal it was never supposed to touch.
Exactly. Machinists refer to this as tracking delay or overshoot.
Overshoot.
Yeah, and it causes a multitude of surface defects. It leaves ripples along the edge of the cut, and it causes severe corner rounding. Like, if the blueprint calls for a razor-sharp, perfect 90-degree internal corner, the high-inertia machine ends up leaving a sloppy, rounded curve because the table simply couldn't break in time.
Which means the part is out of tolerance and goes straight into the recycling bin.
Yeah, ruined. If we connect this to the bigger picture, this cornering problem is really a battle between the physical mechanics and the software's feedback loop.
How so?
Well, a CNC machine operates on constant feedback. The computer checks the tool's position against the blueprint thousands of times a second. This is the position loop. With a moving beam GMC, the moving mass is so low that the servo motors don't have to fight a massive load to make a micro correction.
Because the motor isn't fighting that dump truck level of momentum, so the software can actually trust the hardware to execute the command instantly.
Yes. The software can employ much higher position loop and velocity loop gains. Instead of the computer having to proactively slow the machine down way before a corner just to be safe, it can send faster, far more aggressive electrical signals to the motors.
And the lightweight beam just responds.
Instantly. If you tried to send those same aggressive signals to a heavy-moving table, the sudden torque would cause temporary elastic deformation.
Elastic deformation. Basically, the metal frame of the machine physically bending under the sheer force of trying to stop too fast.
Yeah, the heavy mass forces the steel to flex. With the lighter beam, you eliminate that flex. You brake faster, you reverse faster. Small, intricate arcs are tracked perfectly without radius errors.
So you actually get to use the speed.
Exactly. The manufacturer gets to utilize that 40 meter per minute speed instead of constantly throttling down to baby a heavy table around every single curve.
Okay, so we've engineered the motion, the machine accelerates flawlessly, and it takes corners like a sports car. But that speed triggers a totally different violent chain reaction at the exact point of contact.
No.
The very tip of the spear, where the spindle is aggressively chewing through solid aluminum. The sources highlight two major destructive forces born from this speed: vibration and heat.
Let's talk about vibration first. High-speed milling relies on spindle rotations ranging from, 10,000 to 24,000 RPM.
24,000 revolutions per minute. I mean, the amount of friction being generated is hard to even visualize.
And at 24,000 RPM, even a microscopic structural vibration is disastrous. Vibration causes the cutting tool to bounce imperceptibly against the metal.
Which causes problems.
Big problems. This creates what the industry calls chatter. Chatter leaves rhythmic, visible wave marks all over the finished surface.
Oh, man.
Yeah, if you are machining a casing for a premium laptop or the body of a smartphone, any visible chatter marks render the part completely unsellable.
So how does the architecture of the moving beam actually suppress that vibration?
It's fundamentally about leverage and rigidity. In a moving beam design, the spindle head, the component housing the rapidly spinning cutter, is mounted directly against, or even entirely within, the rigid cast iron structure of the gantry beam.
Okay.
Engineers refer to this layout as having a short spindle overhang.
Ah, I see. It's not sticking out far from its structural support. Like, think about holding a pencil.
Okay.
If you grip a pencil right down near the graphite tip, you can press incredibly hard into the paper and draw a perfectly straight, dark line. The pencil won't bend.
Right.
But if you hold that exact same pencil all the way at the top by the eraser and try to press down with the same force, the middle of the pencil bows, it snaps, or your line comes out totally jagged and uncontrolled.
That analogy perfectly illustrates the mechanics of bending stiffness. A shorter lever arm gripping near the tip drastically increases the structural rigidity.
Makes sense.
Because the spindle is tucked so tightly into the massive gantry beam, it violently resists the lateral forces of the cutter pushing against the aluminum. It exponentially raises the threshold for when chatter can even begin.
Allowing the operator to push the machine harder and faster while still getting that mirror-smooth surface finish.
Exactly.
So what does this all mean for the second destructive force? Heat. Because these electric spindles are spinning at 24,000 RPM. They're generating a massive thermal footprint.
Yeah, a lot of heat.
If the internal mechanics of the machine get too hot, does the metal frame actually warp enough to cut the aluminum in the wrong place? Because in a high-volume factory, a machine wandering off target sounds like a catastrophic design flaw.
Well, this raises an important question about thermal drift, which is honestly one of the most insidious threats in continuous manufacturing. Oh yeah. As metal absorbs heat, it expands. When an electric spindle runs at maximum RPM for a 12-hour shift, it acts like a massive space heater bolted to the machine. If that heat bleeds into the machine frame unevenly, it will literally warp the physical geometry of the structure.
Meaning a part cut at the start of a cold shift might be perfectly intolerant, But the exact same part cut 8 hours later, after the machine is thermally expanded, comes out completely ruined.
Yes. A fraction of a millimeter of thermal growth is enough to completely push a complex aerospace component out of tolerance.
Wow.
But the moving beam architecture mitigates this through a structural design philosophy called thermal symmetry.
Okay, so how does symmetry stop the heat?
Well, it doesn't stop the heat, it controls how the machine reacts to it.
Yep.
These GMCs are built with symmetrical beams, twin supporting columns, and dual-side drive mechanisms.
Oh, I see.
And the spindle is positioned directly in the structural center of this perfectly balanced architecture.
So the heat radiates outward equally.
Precisely. Think about a perfectly engineered steel bridge expanding in the summer sun. Because the structure is perfectly balanced left to right, the thermal energy is distributed evenly.
Right.
As the machine inevitably heats up, it expands uniformly. It grows along a predictable mathematically modeling axis rather than twisting or skewing the critical X and Y geometry.
So it grows in a straight line instead of, like, curling like a dried leaf.
Exactly. And because that growth is perfectly predictable, the machine's active cooling sensors and real-time compensation software can handle the rest.
How does that work?
The software calculates exactly how many microns the spindle has expanded forward, and it dynamically pulls the tool back by that exact microscopic amount in real time.
That is wild.
Yeah, you can run that machine for 3 shifts, 24 hours a day, and the first part off the line will be dimensionally identical to the 10,000th part.
The amount of engineering going into just keeping the tool steady is staggering. I mean, we've designed a machine that accelerates without tearing itself apart, corners without overshooting, suppresses vibration through leverage, and actively compensates for its own thermal expansion.
It's quite the machine.
But this chain reaction of high-speed cutting creates one final, unavoidable physical byproduct. When you shred solid metal at 40 meters a minute, you instantly generate a factory-clogging mountain of metal shavings.
Oh, the avalanche of chips. Managing chip evacuation is arguably the most difficult logistical fluid dynamics challenge in high-volume aluminum production.
The sources make it clear that aluminum chips are uniquely awful to deal with.
Yeah.
Like, they aren't fine, powdery dust. They shear off in these long, curly, wet, razor-sharp ribbons.
Yeah.
They are incredibly sticky, and they are entirely non-magnetic.
Which eliminates the easiest removal method. In steel manufacturing, facilities just utilize magnetic conveyor belts. The magnets simply pull the steel chips right out of the cutting fluid, but aluminum renders magnets entirely useless.
And standard mechanical solutions fail, too.
Completely.
If you try to use a traditional rotating screw conveyor to push aluminum chips, the screw just grabs those long, sticky ribbons and compresses them together. They tangle into dense, rock-hard, burning-hot clumps that jam the motors and completely back up the plumbing.
It's a mess.
Trying to clear that out is like trying to rake wet leaves during a hurricane. You can't just casually brush it away. The machine has to be fundamentally built around the concept of handling the trash.
And that's exactly what the moving beam GMC does. It integrates the evacuation system into the very foundation of its architecture. Because the bed of the machine doesn't have to move, the engineers can utilize widened chain plate conveyors.
Chain plate conveyors.
Yeah, picture a miniature, heavy-duty tank tread running the entire width of the machine's floor. It doesn't compress the chips. It physically catches the bulky nests of metal and carries them straight out of the cutting zone.
But how do you ensure the chips actually make it onto the conveyor? I mean, the spindle is throwing them in every direction at high velocity.
Gravity. Gravity combined with aggressive fluid dynamics. And this is really where the fixed table design reveals its final advantage. Because the massive aluminum workpiece and the table beneath it are completely stationary, the architectural space beneath the cutting zone is entirely unobstructed.
Oh, so you actually have room to work with.
Exactly. Engineers utilize this free space to build the machine bed with steep 30-degree internal slopes.
Ah. There are no flat surfaces for the chips to pool or settle on. They hit the angled walls and slide directly down into the tank treads.
Right. The fixed table makes those wide drainage paths possible. But gravity alone isn't enough to combat wet, sticky aluminum ribbons. The machine also incorporates high-flow nozzles and massive high-pressure flushing systems.
It's essentially an industrial pressure washer built directly into the machining enclosure.
Pretty much. It constantly blasts the chips down the slopes before they have a chance to tangle up and form a nest. But of course, this creates a secondary fluid dynamics problem. You are blasting hundreds of gallons of expensive cutting coolant to move these chips. The result is a massive, fast-moving soup of wet metal and liquid.
You can't just dump that. You need the coolant filtered and pumped right back into the high-pressure nozzle.
Exactly. The fluid management system requires sophisticated separation. As the slurry of wet chips is carried away, the machine employs vibrating screens and cyclone separators.
Sounds intense.
It is. The vibrating screens shake the larger, solid chips loose from the liquid. The remaining coolant, which is still full of microscopic aluminum dust, is pumped into the cyclone separators.
To spit it out.
Yeah, these separators spin the liquid at incredibly high speeds. They use centrifugal force to pull the heavy metal dust to the outside walls while the clean liquid remains in the center.
Oh, wow.
It efficiently separates the sludge, dries the heavy chips for recycling, and recovers perfectly clean coolant to be blasted right back at the spindle.
The sheer complexity of the plumbing alone is wild. And every single aspect of that fluid evacuation system, the 30-degree slopes, the tank treads, the centrifugal separators, is only physically possible to integrate because the massive block of aluminum isn't moving back and forth over it.
It's a profound lesson in causal engineering.
Yeah.
By making the foundational decision to move the bridge instead of the table, you solve the inertia problem.
Right.
Solving the inertia problem allows for aggressive high-speed cornering without overshoot. Tucking the spindle into that rigid bridge suppresses chatter. Centering it creates thermal symmetry, and locking the table down opens up the physical space required to manage the massive volume of chips.
Everything is connected.
Every subsequent problem is solved by the initial architectural choice.
The hidden symphony of physics and fluid dynamics happening inside these enclosures is just incredible. I mean, the next time you pick up a perfectly machined piece of aluminum, whether it's the sleek unibody of your laptop or the structural frame of your car or even the smartphone in your pocket, think about the invisible forces that shaped it. We take these flawless, mass-produced metal objects entirely for granted.
We really do.
But now you know the intense microscopic ballet of thermodynamics and motion control that makes it possible to mass-produce them perfectly.
Understanding the mechanisms behind the manufacturing floor just fundamentally changes how you perceive the physical, engineered world around you.
It really does. And it leaves me with one final thought, something for you to ponder on your own long after we sign off today. The core principle we unraveled in this deep dive is that to achieve blistering speed and absolute precision on a massive scale, you must keep the heavy, unpredictable object perfectly stationary and only move the lightweight, predictable tool around it. If that architectural philosophy is the ultimate key to revolutionizing metal manufacturing, how soon will we see this exact same moving beam physics scale up to other massive industries? Could this same logic be the key to giant gantry systems 3D printing entire skyscrapers? Or, zooming all the way in, could it solve the latency and tracking issues in microscopic robotic surgery? If we can master the physics of motion by flipping what moves and what stays still, what massive engineering challenges will we conquer next?